Welcome back to Honors Calculus. In this video, we're going to be looking at the idea of completeness. And with this, we're going to be finishing a discussion that we started much earlier in the course. You may remember that when we were looking at sets of numbers, I defined the real numbers as a complete ordered field with the rational numbers a subset of the real numbers. That is the definition of the real numbers. We looked at building up the natural numbers, the integers, the rational numbers. We talked about the fact that there's this weird jump between the rational numbers and the real numbers. I gave this definition. We talked about the properties of a field, the closure, commutative, associative, identities, inverses, distributive property that you're accustomed to working in algebra. We talked about making a field ordered by establishing an inequality relationship, and we found a definition that we could use to set up what it means to be less than. We haven't yet talked about what it means to be complete. And so that's what we're going to be doing in this video. Before we can get to that, we need another somewhat related idea, or a foundational idea, which is called bounded. I'm going to denote using the Blackboard bold R here. In theory, this is any field, but in practice, this is going to be the real numbers that we're building up to. So if you think of it as the real numbers, that's fine, but any field will work here. So we say that S is bounded above if and only if there exists some value B in the field, in the real numbers, such that X is less than B for every value of X in S. Or more simply, we can find a number so that everything in the set is smaller than that number. Right? We will call B here an upper bound on the set S. And the vocabulary there is important, specifically an upper bound. There are a lot of options. For example, if I look at a relatively simple set, the set containing the numbers 1, 5, 7, and 11. I'm sorry. As I'm writing this out, I'm noticing that was supposed to say less than or equals. The or equals part, it looks like my touchscreen didn't really grab. All right. And that's important here. Because the number 11 is an upper bound on S. S is a very small set, we can show that by exhaustive proof, right? 1 is less than 11, 5 is less than or equal to 11, 7 is less than 11, and since 11 is equal to 11, it is in fact true that 11 is less than or equal to 11. Here's the issue with this definition. "43 is also an upper bound on S." Where did I come up with 43? I pulled it out of thin air. I found a number. It is a real number. And I know that 1 is less than or equal to 43. 5 is less than or equal to 43. 7 is less than or equal to 43. And 11 is also less than 43. So once again, by exhaustive proof, we can see that 43 works as an upper bound. So would 72, 168, 5,280, 7,654,321, 10 to the 100 power, 10 raised to the power of whatever that number is. These are all upper bounds on S. And so upper bound in and of itself is not all that useful of an idea. And since upper bound in and of itself isn't all that useful, we're going to specify and we're going to look for an upper bound of interest. And we will call that thing the least upper bound, or LUB. I've seen some people pronounce it as lub. I'm going to always refer to it as the least upper bound, or the LUB. Um, I'll also mention here that some mathematicians use the word supremum for this. Supremum and least upper bound are synonyms. Supremum is much harder to remember because it's a weird Latin word that you have to remember the meaning to. Least upper bound is a very evocative word, right? It says exactly what it means. The least upper bound is the one that is smaller than every other upper bound. And so that's why I use that terminology. Least upper bound is fairly easy to remember. All right, I'm going to write this as a theorem, although I'm not going to take the time to prove it. if an element of a set is in fact the least upper bound of that set, or if an element of a set is in fact an upper bound of the set, then that must be the least upper bound. And in that case, we will also refer to B as the maximum of S. All right. So if the least upper bound is an element of the set, we give it a different name. We call it the maximum. Mostly that's just as a way of distinguishing. For what we're going to be doing a little bit later on in this course, being able to distinguish whether or not the least upper bound is an element of the set, or more generally, whether or not an element of the set serves as an upper bound, is going to be a useful tool for us. It's going to be something we're really focusing on. So thinking about things in terms of maximums is going to be a useful property in and of itself. That's why it's worth having a separate name for that. But before we continue onward, I want to look at the other side of things. Because if we can bound something above and find a least upper bound, we can also flip that completely on its head and bound something below. And the same process is going to still work out. All right, it's all the same language over again, so that's why I'm going through it fairly quickly this time. We say that S is bounded below if and only if there exists some element of the real numbers, so that that element is less than or equal to S for every element X in S. Everything in X is bigger than some floor value. We call that value a lower bound of the set. A set can have infinitely many lower bounds, so we're generally interested in the greatest lower bound, which is the lower bound that is bigger than every other lower bound. Again, there's a couple of different names for this guy. Greatest lower bound is the one that is more evocative. It's easy to remember, so that's why we're going with that one. Sometimes we see this referred to as the GLB. I have seen people pronounce it as the glub. I am not going to do that, but it is a thing. You'll also see this concept referred to as the infimum, or the INF of S, which again is extra terminology for the sake of extra terminology. If we have two names, one is easy to remember and the other is hard to remember, why should we spend time looking at the one that's hard to remember? And then finally, if we have a lower bound, which is actually an element of the set, then that lower bound must be the greatest lower bound, and we will call that thing the minimum. All right, so the same ideas that we've had previously. Let's write it in the other order. When we started talking about interval notation much earlier in the course, we described some intervals as bounded and other intervals as unbounded. Now that we have a definition, let's make sure that we actually got something that makes sense. I claim here that the bounded interval from 5 to 7, is in fact bounded. All right, so a set is bounded if and only if it is both bounded above and bounded below. We can determine that a set is bounded above and bounded below by finding an upper bound and a lower bound. In this particular case, that's fairly straightforward. Using the definition of interval notation, the interval from 5 to 7, set up like this, is the set of all x's in the real numbers such that 5 is less than or equal to x is less than 7. Five is pretty obviously a lower bound because for everything in this set, 5 is less than or equal to that thing by the definition. And likewise, we have in the definition that x is less than 7, which means that it's also true that x is less than or equal to 7, which is what it takes to say that 7 is an upper bound. We found a lower bound, we found an upper bound. That's what it takes to say that a set is bounded. Yes, it really is that straightforward. that idea is the last piece that we need in order to finally get to the whole point of all of this. An ordered field is called complete if and only if every non-empty subset of that field, which is bounded above, has a least upper bound. And again, it's beyond the scope of the course, so I'm going to state it without proof. But if that is the case, it is also going to be the case that every subset which is bounded below has a greatest lower bound. Right? The existence of the least upper bound and the greatest lower bound is what leads to this idea of completion. All right, I'm getting very sloppy with the definitions at this point because, again, the specifics aren't all that interesting. But the completion of a field is a set which contains all of the upper and lower bounds. So, for example, we know that pi is not a rational number. That's one of the reasons that pi is so interesting. But any number that can be written with finitely many decimal points, or many places after the decimal point, is a rational number. 3 is a rational number. 3.1 is a rational number. 3.14 is a rational number. 3.141, 3.1415, 3.14159, and at that point, I'm going to give up. All of these things are rational numbers. And so if I create a set which is sequentially the digits of pi, each number adding one more digit in. So 3, 3.1, 3.14, 3.141, 3.1415, 3.14159, and we keep going. 3.1415992, 3.1415926, and so on and so on and so on. Each of the numbers in this set is getting closer to the value of pi because I'm putting in one more digit at the end, one more digit after the decimal point. So it's coming ever so slightly closer. But each of the numbers in this set has finitely many digits. So each of the elements of this set is a rational number. But because we're going infinitely far, we are going to, in the end, essentially have infinitely many digits. And when we have infinitely many digits, we actually have pi. So pi is not an element of this set, but it is the least upper bound of this set. And so this is why the rational numbers are not complete, because you can do things like this. You can take rational approximations by truncating digits, right? That's something I have to stress. We're truncating digits, not rounding, right? 3.14159. That 9 says round the next thing up, and the approximation would be 3.1416, not 3.1415. But 3.1415 has the nice property of being smaller than pi. So we're truncating digits so that each approximation is smaller than the value of pi, and we're coming up and creeping up to the value of pi closer and closer every step. All right. The fact that we can do that and everything in there is a rational number, but the least upper bound is not a rational number, is why the rational numbers are not complete. But because we can do that and we can figure out a way to describe that thing, we give it that label of an irrational number, and we gather all of the irrational numbers together. We put them together with the rational numbers. We call it the algebraic completion of the rational numbers, and more simply, we call it the real numbers. It turns out that any well-defined field, well-defined ordered field, right? So if you have a set which satisfies the properties of a field, you can define an ordering relation on it, and then you take the algebraic completion of that set. No matter what set you started with, you will get something that behaves exactly like the real numbers. So the real numbers are the only complete ordered field that there is. What I mean by behaves exactly like is really kind of interesting. There are other things you can do, but there's a nice one-to-one correspondence. You can swap out all of the symbols and structures in the other set, replace it with real numbers, and everything works nicely. Once again, that's beyond the scope of what we're going to be doing here. This is the lesson that really scrapes at the edge of if you're going onward to study mathematics, eventually you'll take a course called Real Analysis. And in Real Analysis, you will spend the entire semester looking at this idea. The real numbers are a complete ordered field, and breaking it down into some really tiny parts and getting into all of the details that I'm glossing over. For right now, trying to get to you the sense of what I mean when I say that the real numbers are a complete ordered field is all that I care about. So now that we've established this idea of what it means to be complete, what it means to be a complete ordered field, we can wrap up looking a little bit more at bounded and unbounded sets. Because I just realized that I've never defined unbounded. So let's get back to that. All right, an unbounded set is a set which is not bounded. We talked about unbounded intervals, things like the interval from -5 to positive infinity. And when we look at this set, any number you try, remember the set interval from 5 to infinity is defined as the set of all x in the real numbers such that x is strictly greater than -5. For any potential upper bound b, we know for certain, based on the definition here, that we're going to pick a value where -5 is less than b. But we also know that we can pick a value of x in the real number so that -5 is less than b is less than x. And that means that x is in this interval from -5 to infinity. So b is not an upper bound, right? So this interval is in fact unbounded. And with that, I'm going to reach this one that I would like you to try. I would like you to look at the interval from -infinity to +5. Right? This is the other form of an unbounded interval that we've talked about. And I would like you to take a little bit of time to demonstrate that this is also an unbounded interval. Look at what we did in the last example and see if you can copy that logic here. See what you can do with that, and I'll see you in the next video.